This research paper introduces a novel deep learning-based approach for structural health monitoring (SHM) that addresses the issue of missing data in time series data. The proposed method utilizes long short-term memory (LSTM) model and dropout mechanism in the autoencoder framework to identify damage in structures. The inputs channels are randomly dropped during training to simulate missing data, and reconstruction errors are used as the loss function and damage indicator. The effectiveness of this method is demonstrated using the quasi-static response, cable tension, of a cable-stayed bridge from the first IPC-SHM dataset. The results show that missing data imputation and damage identification can be performed simultaneously in a unified manner. The paper begins by discussing the importance of data-driven methods in SHM, which rely on mining inherent patterns in data collected by SHM systems. It highlights the potential of machine learning and pattern recognition techniques, particularly deep neural networks, to approximate nonlinear mappings for correlation mining. However, it notes that these methods often overlook the problem of missing data, which is common in SHM and other real-world applications due to sensor malfunctions, data transmission errors, or other issues. To address this limitation, the authors propose a robust deep learning-based damage identification approach that considers missing data. They employ an LSTM model and dropout mechanism within an AE framework. During training, input channels are randomly dropped to simulate missing data, and reconstruction errors are used as both the loss function and damage indicator. This approach allows for simultaneous imputation of missing data and damage identification. The authors validate their proposed method using the quasi-static response, cable tension, of a cable-stayed bridge from the first IPC-SHM dataset. They find that the missing data imputation and damage identification can be successfully implemented together in a unified way, demonstrating the effectiveness of their approach. In conclusion, this paper introduces a novel deep learning-based method for SHM that effectively handles missing data. By leveraging LSTM models and dropout mechanisms in A frameworks, the authors provide a robust solution for damage identification in structures, even when dealing with incomplete datasets. This research contributes to advancing the field of SHM by addressing a significant challenge posed by missing data in time series data. In structural health monitoring, SHM, missing data poses a significant challenge, impacting the performance of data-driven methods. There are three types of missing data: discrete missing at random time points, continuous missing of continuous time points, and continuous missing of the whole channel. Missing data imputation methods, including model-based and deep learning-based approaches, have been developed to estimate missing values from available data. Model-based methods employ statistical models, such as compressed sensing, singular value decomposition, likelihood-based, and nearest neighbor-based methods. Deep learning-based methods utilize neural networks, including recurrent neural networks, denoising autoencoders, convolutional neural networks, and generative adversarial neural networks. However, most research focuses on discrete and continuous missing data types, with continuous missing data rarely considered. Furthermore, most imputation methods are used as preprocessing and normalization procedures, failing to add additional information during imputation. This paper proposes a robust deep learning-based damage identification approach for SHM, addressing these limitations. The approach employs an autoencoder framework, leveraging long short-term memory, LSTM, to construct encoder and decoder modules. The data reconstruction error serves as the loss function and damage indicator. The proposed method is validated using the cable tension data from the first international project competition for structural health monitoring. During training, channels of the inputs are randomly dropped to simulate missing data, and the LSTM structured autoencoder model attempts to reconstruct data of all channels. This approach enables the model to learn inner relationships among monitoring data of different channels and extract hidden representations. The proposed method is organized into sections, introducing the basic modules, open-source dataset, preprocessing procedure, and implementation details. The results demonstrate the effectiveness of the proposed method in handling missing data and identifying damage in SHM. In contrast to conventional deep neural network (DNN) models, the proposed approach provides improved performance in reconstructing missing data and detecting damage. This paper highlights the potential of deep learning-based methods in addressing missing data challenges in SHM and paves the way for future research in this area. Deep neural networks, defined as neural networks with more than one hidden layer, are designed to learn effective representations that extract nonlinear relationships hidden in data through end-to-end training. A typical DNN model consists of an input layer, multiple hidden layers, and an output layer with densely connected units. Information flows from the input layer to the output layer, generating predicted outputs. The training process involves adjusting model parameters to minimize the loss function, typically using the gradient descent method and backpropagation algorithm. However, the large parameter space in DNNs can lead to overfitting issues. To address this, dropout mechanisms have been proposed as a standard technique for training deep neural networks. Dropout randomly ignores some units during training by enforcing their weights as 0 with a probability of p, reducing connections in the neural network and helping to prevent overfitting. The forward propagation process in a DNN is mathematically represented as the calculation of the hidden state of the LTH hidden layer based on the input dataset and model parameters. The loss function, such as mean square error, MSE, is defined to evaluate the prediction performance of the DNN model. Parameters are updated using the gradient descent method, with the gradient of the loss function with respect to the parameters being calculated and backpropagated to the parameters of all layers. In summary, the architecture and training of DNNs involve the use of dropout mechanisms to prevent overfitting, mathematical representations of the forward propagation process and the loss function, and the backpropagation algorithm for parameter updating. In the realm of neural networks, overfitting is a common issue that can lead to poor generalization. To combat this, the concept of dropout has been introduced as a regularization technique. By randomly ignoring units in the input layer during training, the model learns invariant patterns even when data is missing. This approach is particularly beneficial in missing data imputation tasks, where random missing channels can negatively impact a well-trained network. Dropout can be viewed as adding unbiased noise to hidden units, making it a form of ensemble learning. The authors emphasize the importance of applying dropout in both early and late stages of the training process to avoid overfitting and underfitting. Figure 1 illustrates the conventional dense neural network, DNN, and the DNN with dropout units, showcasing the direction of information flow. The discussion then turns to long short-term memory, LSTM, networks, which are well suited for modeling temporal relations in time series data. Unlike conventional DNNs, LSTMs introduce recurrent connections to the hidden layers, allowing them to capture temporal correlations. Figure 2 illustrates the unfolded expression of a deep RNN model with multiple layers, where rectangular blocks represent hidden layers and cyclic arrows denote recurrent connections. The authors employ LSTM as the correlation model in this study, citing its efficiency in modeling sequence data. The LSTM model consists of LSTM cells with gate units, as depicted in Figure 4c. The updating of LSTM units and their parameters are governed by equations 6 and 7, which are not explicitly stated on this page. The use of dropout in the input layers during training is a novel approach, as it simulates the missing data condition and enforces the model to learn invariant patterns. This technique is particularly relevant in missing data imputation tasks, where random missing channels can harm a well-trained network. The author's approach combines the benefits of dropout and LSTM to develop a robust model for handling missing data. The page concludes by highlighting the importance of LSTM in modeling temporal relations and its suitability for this study. The discussion sets the stage for the development of a novel model that integrates dropout and LSTM to address missing data imputation tasks. Recurrent neural networks, RNNs, are designed to process sequential data, comprising an input layer, hidden layers, and an output layer. The hidden layers maintain the network's memory, enabling it to capture temporal dependencies. A variant of RNNs, long short-term memory, LSTM, cells, are specifically tailored to learn long-term dependencies. LSTMs employ gates, input, output, and forget gates, to regulate the flow of information into and out of the cell state. The computations governing these gates, cell state, and hidden state are described by equations 5, 6, and 7. In addition to RNNs, the autoencoder A framework is an unsupervised learning method for representation learning. An AE consists of two modules, an encoder and a decoder. The encoder compresses input data into a lower dimensional space, while the decoder reconstructs the original input from this compressed representation. The AE's objective is to minimize the reconstruction error, as expressed in equation 8. This is achieved by training the model to find the optimal parameters theta that minimize the difference between the original input x and the reconstructed input g, f, x. Autoencoders have gained popularity in learning meaningful representations of complex data without explicit supervision, by minimizing the reconstruction error between the input and output. This compressed representation captures the underlying structure of the input data and removes redundant information. In structural health monitoring, SHM, the learned compressed representation and reconstruction errors are used as damage indicators. A novel approach is proposed, integrating an LSTM structured autoencoder, comprising two stages: the LSTM structured encoder module, which learns the underlying relationships in hidden compressed representations, and the LSTM structured decoder module, which learns to reconstruct the inputs from the hidden representation. Linear layers are added to the LSTM cell to reshape the output size of the encoder and decoder. This architecture enables the model to capture spatiotemporal relationships among time series data from multiple channels. To simulate real-world scenarios, the model is trained on augmented data with artificially introduced missing values, equivalent to adding unbiased noises to the training dataset. This approach allows the model to learn robust representations and relationships among the data, making it suitable for applications with incomplete data. The proposed model remains unchanged when missing data occurs, ensuring its reliability in real-world applications. A case study is presented using an open-source cable tension dataset from an in-service cable-stayed bridge, released in the first IPC-SHM. The dataset comprises monitoring data from 14 cables over 10 days, with a sampling frequency of 2 Hz, and includes a week-long period in 2006 and 3 separate days in 2007, 2009, and 2011. One cable is intentionally damaged, and missing data occurs in 3 cables in 2011. This dataset provides a challenging scenario to evaluate the model's performance in detecting damage and handling missing data. Figure 3 illustrates a cable-stayed bridge with red cables representing the 14 cables in the released dataset. A typical monitoring cable tension time series is shown in Figure 4, featuring low-frequency trends induced by temperature and high-frequency peak points induced by vehicles. The monitored cable tension can be decomposed into 4 components: dead load, temperature, vehicle, and noise effects, represented by the equation total T equals dt plus Et plus Vt plus Rt. The vehicle-induced cable tension is modeled using the moving concentrated force assumption, expressed as a matrix equation, equation 9. For a single vehicle, the cable tension of the ITH cable is given by equation 10, which depends on the discretized location of the vehicle and the influence surface of the vehicle, represented by eta I, n, x, t, y, t. In the presence of multiple vehicles, the vehicle-induced item of the ITH and JTH cable is given by equation 11, which sums the contributions of each vehicle. This equation provides a single vehicle-based cable tension ratio as a damage indicator. The authors have thus far presented a mathematical framework for modeling the vehicle-induced cable tension in a cable-stayed bridge. The decomposition of the monitored cable tension into its components and the modeling of the vehicle-induced cable tension using the moving concentrated force assumption provide a foundation for further analysis. The discretized flexibility matrix D and the influence surface eta I, n, x, t, y, t are critical components of the model, as they capture the structural properties of the bridge and the relative stiffness of the stay cables. The authors have also highlighted the importance of considering multiple vehicles on the bridge, which is a more realistic scenario. The next section will likely discuss the preprocessing of the data, which is essential for further analysis and damage detection. The authors may discuss the filtering of the data, removal of noise, and other preprocessing techniques to prepare the data for the damage detection algorithms. Decoupling the vehicle-induced term of cable tension from multi-source effects is essential for load test style response information, but its non-stationarity poses a challenge. Figure 5a-b illustrates this complexity. To address this, smaller segmentations are recommended, leveraging the sparsity of vehicles on the bridge. Since most observed data points are near the trend term induced by temperature, a violin plot is employed as a detrending technique. This visualization combines features of box plots and kernel density plots, displaying the distribution of a continuous variable across different categorical levels. The violin plot facilitates identification of the trend term, and the median value of a specified segmentation is used as the trend term. Figure 4b demonstrates the obtained trend term in a 30-second segmentation using this method. The whole-day scaled trend term is obtained through segmentations and interpolation, assuming a smooth temperature-induced trend term. This is illustrated in Figure 4d. The multi-source effects of typical cable tension time series and trend item based on violin plots are presented in Figure 4. The detrending process enables the separation of the vehicle-induced term from the overall cable tension signal. By applying this method, the effects of temperature and vehicle-induced load can be isolated, providing valuable insights into the structural behavior of the bridge. This approach is particularly useful for structural health monitoring and load test analysis, as it allows for the accurate estimation of the vehicle-induced term and its impact on the cable tension. The proposed model's implementation details are discussed, focusing on the vehicle-induced cable tension dataset. As vehicle loads remain identical, their relationships are determined by influence surface and relative stiffness. This allows the model learned from a specific period to form an agent model of that period, enabling the inference of changed structural conditions when the model changes in another period. The reconstruction error predicted by the pre-trained baseline model of a specific period can be used as a damage indicator. The proposed model learns spatiotemporal relationships among monitored data of all channels using an LSTM structured autoencoder, represented by the equation A v underscore I t equals theta v underscore I t plus tau v underscore I t. The input and output nodes are defined, and the pseudocode for the training procedure is provided. Training involves initializing parameters, specifying batch size, sequence length, and learning rate. The atom optimization algorithm is employed to train the model. The model architecture consists of a 3-layer LSTM structured encoder and decoder cells with 32 units in each layer. Linear layers are added to satisfy the shapes of the hidden layer and output layer. Hyperparameters are set as follows. T equals 2400 max underscore iteration equals 10000 batch underscore size equals 30 and alpha equals 0.005 The model is built on TensorFlow, and the optimizer is Atom. A comparison model, consisting of a 3-layer DNN with 64, 32, 5 hidden units and a decoder structured by a 3-layer DNN with 5, 32, 14 hidden units, is also developed. The results and discussions of the experiments are presented in the following section, where 012 cables are simulated to be dropped, corresponding to a 085.7% missing rate, in the training process. A comparative analysis of the training performance of DNN structured and LSTM structured autoencoder models is presented, focusing on their robustness under varying data loss rates. Figure 5a illustrates the loss curves of both models with a 50% data loss rate, equivalent to 7 randomly missing cable data points. The training errors of DNN and LSTM networks under different data loss rates, shown in Figure 5b, reveal an exponential increase in training performance with the rise in data loss rate or the number of missing cables. The LSTM structured A model outperforms the DNN structured A model due to its ability to form a memory of historical data, enabling the extraction of spatiotemporal correlation features of cable forces in the cable group. This superiority is attributed to the LSTM model's capacity to leverage temporal information to better predict and reconstruct missing values. Figure 6 presents the prediction results of the pre-trained LSTM network for cable tension on November 1, 2011, where cable tensions for SJX08, SJS13, and SJX13 are actually missing, and cable tensions for SJS08, SJS09, SJS11, SJX11, SJX12, SJS13, and SJX13 are dropped out. The results demonstrate the LSTM structured A model's effectiveness in reconstructing missing data and diagnosing cable health based on the pre-trained agent model of the cable group's initial performance. Notably, the real cable tension value of cable SJS11 in Figure 6c is lower than the benchmark prediction value, indicating a decrease in the actual carrying capacity of the cable and suggesting cable damage, consistent with the cable state evaluation results released in 14. A comparative analysis of 3 distinct scenarios is presented, examining the effects of varying assumptions on the outcomes and impacts of 2 variables. Scenario A compares SJS08 and SJX08, both assumed to be losses, to elucidate differences in outcomes when both variables are considered as losses. Scenario B compares SJS09 and SJX09, with SJS09 assumed to be a loss, exploring how outcomes change when one variable is assumed to be a loss while the other is not explicitly defined as such. Scenario C compares SJS11 and SJX11, both assumed to be losses, with SJS11 also considered as damage, investigating the implications of considering one variable as both a loss and damage, while the other is only viewed as a loss. These comparisons aim to understand the effects of different assumptions on the variable's outcomes and impacts, providing insights into how varying assumptions can influence the interpretation and analysis of data in various contexts. By examining these scenarios, researchers can gain a deeper understanding of the sensitivity of their findings to different assumptions and develop more robust models that can accommodate various scenarios. This analysis contributes to the broader understanding of how assumptions shape our perception of data and its implications for decision-making processes. The comparisons are crucial for researchers to comprehend the sensitivity of their findings to different assumptions, enabling the development of more robust models that can accommodate various scenarios. The analysis highlights the importance of considering the implications of different assumptions on the interpretation and analysis of data, ultimately informing decision-making processes. A comparative analysis of the proposed model's performance on the SJS14 and SJX14 datasets reveals its effectiveness in handling missing data. Figure 6 illustrates the prediction results of the deep neural network (DNN) and long short-term memory (LSTM) models in the 50% data loss rate case on November 1, 2011. The results demonstrate the superiority of the LSTM structured autoencoder (A) model in handling missing data. Figure 7 shows the diagnosis results of the cable group based on the 3 sigma criterion, indicating that only cable SJS11 is damaged, while the other cables are in a healthy condition. This finding is consistent with the cable state evaluation results presented in 14. The diagnosis is performed using the standard values of the prediction error calculated from the pre-trained LSTM structured A model. The proposed approach addresses the missing data issue in structural health monitoring (SHM) by employing the dropout mechanism to develop a robust model for damage identification. This approach eliminates the need for standard missing data imputation preprocessing and downstream tasks. Key findings include 1. Unsupervised learning representations learned from the LSTM structured A model form a baseline agent model for the correlationship of a group of cables. The reconstruction error can be used as a damage indicator. 2. The baseline model for the cable group establishes a many-to-many spatiotemporal mapping model for cables in the group, improving the efficiency of SHM data processing and health diagnosis. 3. The unsupervised learning representation of the LSTM structured A model and the dropout mechanism employed in this paper can loosen the requirements of data quality, missing data occasion, while achieving an accurate and robust baseline agent model. The proposed approach demonstrates its effectiveness in handling missing data and improving the efficiency of SHM data processing and health diagnosis. The use of the LSTM structured A model and dropout mechanism provides a robust and accurate baseline agent model for damage identification and other tasks. These findings contribute to the development of more effective SHM systems. The authors acknowledge the financial support from the National Natural Science Foundation of China and express gratitude to the organizations that provided invaluable data from actual structures. This research focuses on the development of a novel framework for assessing the seismic performance of reinforced concrete structures. The proposed methodology integrates advanced numerical simulations and machine learning algorithms to predict the probability of failure under various seismic intensity levels. The study employs a hybrid approach, combining finite element modeling and artificial neural networks to simulate the nonlinear behavior of structures. The finite element model is validated using experimental data from actual structures, ensuring the accuracy of the simulations. The artificial neural network is trained on a large dataset of structural responses, enabling the prediction of failure probabilities with high precision. The authors introduce a novel seismic intensity measure, termed the seismic damage index, which takes into account the structural response under various loading conditions. This index is used to quantify the damage state of the structure and predict the probability of failure. The results show that the proposed framework accurately predicts the seismic performance of reinforced concrete structures, outperforming traditional methods. The study highlights the significance of considering the nonlinear behavior of structures in seismic performance assessment, as well as the importance of integrating advanced numerical simulations and machine learning algorithms. The proposed framework has the potential to improve the design and assessment of reinforced concrete structures, ensuring enhanced resilience to seismic events. Future work includes expanding the dataset to include more structural types and exploring the application of the proposed framework to other types of hazards. This video presents a comprehensive list of research papers that have significantly contributed to the field of computational biology. The papers are organized chronologically, starting from the early works in the 1960s and continuing up to the present day. The first section covers the foundational studies on genetic algorithms and evolutionary computation, which laid the groundwork for the development of computational biology as we know it today. Key figures such as John Holland and David Goldberg are highlighted for their pioneering work in this area. The second section delves into the advancements made in the 1980s and 1990s, including the introduction of neural networks and their application to biological systems. Researchers like Johann Pao and Robert Hecht Nielsen are recognized for their contributions during this period. The third section focuses on the explosion of computational biology in the 21st century, driven by the rapid progress in genomics, proteomics, and bioinformatics. Papers by influential scientists such as David Haussler, Richard Durbin, and Michael Waterman are featured for their impact on the field. The final section discusses the current state of computational biology, emphasizing the integration of machine learning, deep learning, and artificial intelligence techniques into biological research. Notable researchers in this area include David Baker, Aviv Regev, and Jennifer Doudna. Throughout the video, key terms and concepts are explained in detail, ensuring that viewers gain a thorough understanding of the subject matter. The significance of each paper is also discussed, providing context and highlighting the impact of these studies on the development of computational biology.